without facts for guidance. Now it's time for a little science.
Guess what? This is exciting. An atom has been observed existing in two places at once. Now, this is crazy talk. Thank you, Mike. I'm so glad that you can hear the jingles, because I can't hear the jingles. It's, again, tech. But as long as I can hear my guest who's coming on in 6 minutes, then we're going to be fine. Okay? So this is quantum physics. This is very exciting. Now, quantum tends to deal with things in a really teeny tiny, like photons and particles, teeny tiny. But scientists at the Australian National University have carried out an experiment showing that two helium atoms can behave as quantum waves spreading across space while their motions remain linked together, and essentially find them in two places at once, which is amazing. The experiment did not create one atom splitting into two copies, just to be clear. Instead, researchers produced a pair of atoms that shared a single quantum state. Each atom behaved according to quantum mechanics, meaning its position was not fixed, but described by a probability wave, showing where it could be found. And this is that whole thing about if you shine a light on an atom, you suddenly, it's all about measurement. Like, atoms do one thing when they're being watched and another thing when they're not being watched, okay? Like naughty children, right? Like my youngest. You sort of, they're doing something, they're writing on the wall, you turn around, you can never spot them, like a teacher on the blackboard, right? So they're existing in a wave. Now, when physicists say atoms exist like a wave, they mean that the atom is mathematically spread over many possible locations, because that makes a lot of sense, doesn't it? Each location has a probability. How likely is my kid to be at the mall versus at Pizza Express versus in Clapham High Street, part of a mob, right? The atom does not have one definite position, though, until it's measured. And when the atom is measured, it acts like a particle. It appears in one specific place, only one outcome is observed, and the spread of possibilities reduces to a single result, right? Now, this change from many possibilities to one detected position is often described as a wave function collapse, all right? Now, what existing in two places at once actually means, before measurement, the atom's probability wave occupies multiple locations simultaneously because it's a wave. The atom is not duplicated, though. Its location is fundamentally uncertain and distributed, all right? And then the experiment confirmed that atoms can move along multiple paths at the same time. And remember, we had two atoms, so we found that they were linked so that if one moved in one direction, the other did the same thing. So we found that the two atoms were kind of like identical twins, kind of acting in the same way at the same time, so they were connected across time and space. They were quantum entangled in their motion, which means that the two helium atoms were deliberately prepared so their movements were linked. And then measuring one atom's motion instantly gave us information about the other one. And their motions are described by one shared quantum system rather than two independent particles. But this is amazing because atoms are not naturally all entangled. Okay, so we had to create this state, but we did manage to do it. And I'm expressing excitement, and I'll be honest, I don't totally understand it, but I do get that I'm sort of as soon as I heard this, I went, oh, does that mean that we're going to start being able to, like, beam me up, Scotty, right? Which, by the way, for any of you geeks out there, I'm well aware only ever existed in the animation. It was never actually said in the original live action series, but still, beam me up, Scotty. So entanglement is extremely fragile. Interactions with the environment normally destroy quantum behavior, which is a process called decoherence. So researchers therefore had to cool the atoms close to absolute zero, isolate them from disturbances, created them together in a controlled quantum process in order to do this. But really, why is this experiment so important? Well, similar quantum effects have previously been demonstrated mainly with photons, right? But photons don't have mass. Right? This is the first time we've done this with actual mass, with actual, like, stuff, right? These are massive atoms in comparison to a photon. They have mass, they respond to gravity, and they're the closest thing to everyday matter, like us, that we've ever done this with. So, totally exciting. This is the closest thing that kind of links quantum mechanics to general relativity, which explains large-scale structures and gravity. And some possible future implications. testing whether gravity itself behaves quantum mechanically. We could end up with ultra precise sensors and measurement technologies. We could improve quantum technologies and navigation systems. And fundamentally, we could start understanding why large objects stop showing quantum behavior. Because I have never been in two places at the same time. But why not? If helium atoms can do it, why can't I? And by the way, I know I talked about teleportation and stuff. No teleportation or cloning of matter is implied in this, but I still think it's kind of cool, right? Totally cool.